Let's talk about Kirchhoff's current law. One way of stating Kirchhoff's current law is that charge does not accumulate in any component of the circuit. Okay, so for a simple component, let's say consider some arbitrary component. This could be anything: voltage source, current source, resistors, whatever. So let's say we are observing that component for interval delta t, and in that time interval delta t, delta q1 of charge goes into the component and delta q2 comes out of the component on the right hand side. Okay, so if we apply this statement, charge does not accumulate in any component of the circuit. That means the total charge going in should be equal to the total charge going out. That means delta q1 should be equal to delta q2. So, and then if you're observing that for interval delta t, you can divide by delta t on both sides. Note that this delta t can be anything, so you can also apply limits delta t tends to 0. So then from there, what we get is the total current entering any component should be equal to total current exiting the said component. Okay, in other words, the current going in should be the current coming out for all times. All right. So now let's look at a slightly more complicated situation. Let's say there is a node in a circuit and there are three wires attached to that node. Okay, and the currents are I1 of t, I2 of 3, and I3 of t. And in general, this could be any number of wires coming in. Now, if we apply the same statement again at this node, saying charge cannot accumulate at that node, that what that means is then the sum of all the currents going into that node should be equal to 0. So that will give us another way of stating KCL, is the algebraic sum of all currents at any node in a circuit is equal to 0. Okay, and this is the statement of the KCL which we will use in analyzing our circuits, because in most circuits we're dealing with currents and not charge. Okay, so just to say another time, this algebraic sum, that means the sum of all currents entering any node in a circuit, is equal to 0. Okay, so let's and then you can generalize that statement in a bit more general way. Is you can take any part of the circuit. Okay, not just one node or a component. You can take any part of the circuit, and let's say there are some, let's say, 4 wires going in, and this could be any number, right? And in each of these wires there is a current. Again, you can, because the charge does not accumulate, if charge does not accumulate any component, then any part of the circuit also you can say that there is no charge accumulating there, right? So then again, you pick some arbitrary part of the circuit and you say these are the 4 currents going in, or any number of currents going in, then the sum of all those currents should be equal to 0. Okay, and this is a more general way of saying KCL, but probably the most often used version of the KCL will be we're going to apply the KCL at individual nodes in a circuit. Okay, and there will be some very rare cases where we, not really that rare, but there will be cases where we want to apply this more general definition of the KCL. So let's look at KCL at action in a certain circuit. So if you observe this circuit, there are 4 nodes, A, B, C, and D. Let me get rid of this. Okay, so let me first look at apply KCL at node A, right? So remember, KCL is the sum of all currents going into node A should be equal to 0, right? So I will start from I1, right, and then we'll go anti-clockwise and cover all the currents. So if you look at node A, so remember I'm applying the statement, the sum of all currents going into A will be equal to 0. So I1 is going out of A, so that will be minus I1 is going into A, right? Like plus I5 is going into A, minus I4 is going into A, and plus I2 is going into A. Okay, so that means the sum of all this current should be equal to 0. Similarly, I'm applying KCL at all of the nodes. So I would recommend you guys to pause the video here and make sure that you agree with all these other statements, that these 3 other equations mean the sum of currents going into these other nodes is also equal to 0. Okay, so we'll stop here.